Um, all right, so has anybody seen this before? Okay. Who can prove this to me? You know, you could.
Yes.
Did y'all do this in history of math?
No, we did this in
Modern geometry.
Oh. Okay. Well, good.
Definitely.
This is really a review for you guys then. You're really going to be bored in class today. So most students, when you get to Calculus 3, you're still like a sophomore, you know? Like this is not typically an upper level math class at most places. But that's okay. I'm going to go ahead with a plan. And if you've never seen this proof before, then maybe you'd be interested. This is the Pythagorean theorem, and we teach it to like 8th graders, at least how to use it. And you can see examples of this, like 3, 4, 5 triangles or whatever, and sort of be convinced. But if you really wanted to make sure that every single right triangle has to follow this equation, then this is how you could convince yourself. You start by drawing a square. And you say, each one of these angles in the corners, according to how I've chosen to construct this, is going to be a 90-degree angle. You'll have the same angle measure. And the length of the sides is going to be the same. Notice, I haven't specified a particular side length. I'm just saying that it's all the same, whatever I've chosen. And then what you're going to do is you're going to take some measure a little bit out from each of the corners and make a little mark. And again, based on the way you choose to do this, it can be any length if you want, but it just has to be the same distance. And then we're going to connect these up. Oops. And what I'm assuming next is that you have already been convinced of the side-side-side theorem for congruent triangles. And the side-side-side theorem says, as long as these sides, what am I saying? Side angle side. As long as you've got a side and another side and the angle between them is the same, then the triangle is congruent, right? That's like a theorem from geometry. Let's assume that we already know that. Let's assume that since we know this side and this angle and this side are the same for these 4 triangles, that everything about the triangle has to be the same. And I'm going to name this A, and I'm going to name this longer one B, and then I'm going to name this C, and since these are congruent triangles, then this side has to be the same for all 4 of them as well. And again, since these triangles are congruent, I can label these angles, and they should be the same angle. So I'm going to label the angle alpha as the same everywhere. And then this angle beta is the same for all 4 triangles. Okay, everybody's still good. Now, what do you know about the interior angles of a triangle? If I add up the angle measures from all 3 angles in the triangle, the 3 interior angles add up to 180 degrees. And suppose we say that the right angle is 90 degrees, that means alpha plus beta must be equal to 90 degrees. Okay, what about these, what is it? I think it's complementary angles, right? Like if I have a straight line and I have a number of angles that make up the straight line, I think it's called complementary, I don't know. Like right here, I've got alpha plus beta plus some other angle makes a straight line, right? What does that straight line angle have to be? No. Yeah. If I wanted to make a straight line, that has to add up to 180. So this missing piece, that must be 90, right? 90 plus 90 equals 180. And so that means these are also right angles. And that means the shape I've drawn here in the middle is a square. same sides, all 90-degree angles. I've got a little square inside of a big square. Cool. Now I want to calculate the area of the big square. And I'm going to do this two different ways. In the first way, I can calculate the area of this big square is I can just take one of the side lengths and then square it, right? So if I took a plus b squared, that should give me the area of the big square. Another way I could do this is, what's a separate way I could do this? I shouldn't look at the people who already know. I should look at the people who haven't taken modern geometry yet. So you can work out this brain teaser.
Could you add like the middle square area plus the area of the four triangles?
Yeah, very good. So I've got the middle square, which is c squared, plus the area of four triangles, which is 1/2 base times height. Okay, somebody expand this for me. What's a plus b squared? On the right side, what is 4 times 1/2? Do you see it? Cool. And all along, we never said that A or B had to be a specific length or a specific ratio to each other. We said you could arbitrarily select the length of A and B, which means that this equation has to be true for every right triangle. The only thing we really enforced here is that the corners of the big square had to be 90-degree angles. So this works for every right triangle. I like to bring this up at the start of Calculus 3 because we are going to use the Pythagorean theorem very soon. And so it's nice to see, I think. I've got some vocab words for you. For the rest of the semester, if I say scalar, I'm talking about like a single constant number. Like the number 3 could be a scalar. If I were to weigh my water bottle, the mass of this object would be a scalar. Our current definition that we can use for a vector is that it's a list of numbers. So an example of a vector might be something like this, where I've got a list of 3 different numbers, just like this.
Can you post these slides after class?
Yeah, that's a great question. I can post it right now if I think about it. Let me go to our Moodle. Cal 3. Okay. Okay, so on our Moodle, you can find the syllabus. Now you can find the link that says course materials. And when you follow this link, it'll take you to this webpage. And you can get to these lecture notes by clicking the lecture notes link. You can also get the homework assignment here if you want to. And when I'm done recording this video, I'll put the video up.
Do you like ducks a lot?
No. It just is what it is. I needed something to put there. And I didn't have any thumbnail ready to use, and so it's just like a placeholder. But I like your sweater. It's very didn't plan that. But yeah, so that's where you can find course materials the rest of the semester. I'll try to upload the notes there. And so if you want to, I've seen some students like get their iPad and download the PDF of the notes and then take notes over the top of the notes the way that I do during class, if that's what you prefer. But so a vector is a list of numbers, and a lot of times it's useful to describe something with a list of numbers. Like if you have an object that's moving through space, you could describe the velocity of that object with an x component, a y component, and a z component. If you've taken physics classes, you've probably already done this. So that way you can kind of know what direction it's heading in and how quickly it's moving. If I use the word size of a vector or dimension of a vector, then I'm talking about the number of entries. And so I would say this is a three-dimensional vector, where I would say this vector has size 3 just because it has 3 entries in the list. Okay? If you want to add and subtract vectors, you can do so as long as they have the same dimension. You can't subtract vectors of different dimension, but if you do have vectors of the same dimension, then this is really easy. It works exactly how you think it would work. I'll do one example and then we'll move on because I think you guys are smart enough to get the picture. If I wanted the vector u plus v, what is it going to end up?
6, 3,
Okay. So you do addition and subtraction entry-wise. The first entry, the second entry, the third entry separately. What if I want 2u minus 3v? Can somebody tell me what that one's going to be?
8 minus 6, which is 2. 10 plus
10 plus...
10 plus 6. Oh, yeah, I definitely... It's fun putting out
Negative 3.
Okay. So I'll take a pause so that you can really scrutinize this. But if I have a scalar times a vector, then the scalar multiplies every entry in the whole vector. So 2 times 4 is 8, 2 times 5 is 10, 2 times negative 6 is negative 12, and then, negative 3v, that scalar, negative 3, multiplies every entry in the vector v. So negative 3 times 2 is negative 6. Negative 3 times negative 2 is 6. And then negative 3 times negative 3 is 9. And then you add those together like that. Questions? No? Yeah, so hopefully that makes sense. Hopefully it's exactly how you would expect it to be. Now, again, if you've already taken linear algebra, if you've already taken physics, this is going to be a little review for you. But besides just being a list of numbers, a vector could be represented as a little arrow. And I have an extremely high-tech multimedia presentation for you. Okay. Here it is. So, let's say I have a vector that is the vector 2, 4. I could represent this on the xy plane where I just set one of the coordinates to 2 and another coordinate to 4. The tail of the vector is always going to originate from the origin, 0, 0. And then the pointy end of the vector is going to end up on the coordinate 2, 4. Let me have another vector. We'll call it -1, -3, or -1, -3. Make that one a red one. Let me make it a little bit more interesting. I want it to be -1. No, I'm getting all mixed up. What is that really? That's 1, -3. Okay. So what would it look like if I want to add those two vectors? This is the really high-tech fancy part. You ready? I can move one of the vectors so that its tail is on the tip of the other vector, like this. And wherever this ends up, that vector here, the green one is the sum of the first two. So 2 plus 1 is 3, 4 plus -3 is 1. That green vector is the vector 3, 1. Okay? And you'll notice that addition is commutative, which means it doesn't matter what order I add those vectors in. I could do the red one first and then the blue one, and I still get the same sum. Right? If I want to subtract a vector, it's the same thing as multiplying the vector by a -1 scalar, and that points in the opposite direction. Does that make sense? Like, if I want to subtract the blue vector, that would be the same thing as adding this yellow vector. It's the same length as the blue vector, but it's just pointing in exactly the opposite direction. What else? If I wanted to multiply a vector by a scalar, like if I want to multiply this green vector by the scalar 2, then I would end up getting a vector that is twice as long as the green vector pointing in the same direction. That's what 2 times the green vector would look like. Okay. So that brings us to a point. If I use the word magnitude this semester, or the word length, like we're talking about vectors as arrows in space, what's the length of that little arrow? Or if I use the word norm, those all mean exactly the same thing for us this semester. The norm of a vector is like taking the absolute value of a number, but for vectors. The norm is always a non-negative real number scalar. Okay? So if I have a two-dimensional vector, I can take the norm of that vector, which is just the length of the arrow in space, using this. Why? Because of the... Yeah, well, it's like the Pythagorean theorem, right? If I have all right triangles as a squared plus b squared equals c squared, let's say A is lying in the x direction, so it's the x component of the vector. B is lying in the y direction, so it's the y component of the vector. Then C is the length of the vector. And to solve for the length, then you would just take the Pythagorean theorem, take the square root of both sides, and that gives you that formula. By the way, if I'm trying to tell you about a specific entry in the list of numbers, then I'm going to use a little subscript. So the whole vector is named u. The first entry is u1, the second entry is u2. For a three-dimensional vector, you've got a list of 3 numbers. And as a little arrow in space, that would have an x-coordinate, a y-coordinate, and a z-coordinate for where the tip of the vector ends up. And if you want the length of a three-dimensional vector, the formula is really, really similar. And if you want to derive that formula for yourself, what you have to do is first look at only the projection of that 3D vector onto the xy plane. Like, here's my three-dimensional space with x, y, and z coordinates. But what if you look at this space down the z-axis, where you can't really tell how much depth it has, and you only look at like the projection as if you flattened it onto the xy plane? You have to have a good imagination in this course, because I can't draw very well. Okay. So imagine you flatten this three-dimensional vector against the xy plane. Well, now you can take the Pythagorean theorem formula with the x-coordinate, the y-coordinate, and calculate the length of that projection on the xy plane. Then, between that projection and the z-coordinate, you can create another right triangle and apply the Pythagorean theorem a second time to get the true length of the vector in space. Let me try to draw this for you. And I've already warned you that this is going to be a bad drawing, but I'm going to try. So here's x, here's y, here's my z axis. And then I've got this vector that is pointing, kind of back. And it is going to be flattened or projected onto the xy plane. And so this is like the flattened version. This little dotted line only has a z component to it, right? It's only going back into the board. And then this has a y component and an x component. So if I want the length of this orange projection, the length of the orange projection, and let's call it u, is going to be the square root of the x component plus the y component squared. But if I want the length of the actual vector v, then I've got, this right triangle here plus this right triangle here. I'm going to end up using that distance formula, or using the Pythagorean theorem on this right triangle now, which has one side length is the length of u squared, plus the other side length is the z component, and I'm going to square that too. And this is going to be the square root of the x component plus the y component, square root squared, right, plus z squared. Lastly, the square cancels out the square root, and then you end up with just the square root of the x component squared plus the y component squared plus the z component squared to get you the length of the vector I really care about in 3D space. Okay, so that brings us to our formulas. For a two-dimensional vector, add them up just like you would expect. For a three-dimensional vector, it's super easy to remember. And again, it's not easy to close your eyes and imagine like a four-dimensional space. But as mathematicians, when we talk about the norm of a four-dimensional vector, like you've got a list of 4 numbers, we're going to just extend this distance formula, kind of how you would expect we would extend it, by pretending that we do have a 4th dimension, and that the 4th dimension could have a 3-dimensional projection of the 4-dimensional vector, and then using the Pythagorean theorem idea to say, well, I can just add up each entry of the vector squared and then take the square root of it, and it's going to give me the norm of a vector with any dimension I want. The norm of a 4-dimensional vector, 5-dimensional vector, and so on. Okay. If the velocity of my pool ball is sitting on a pool table, so that's like a 2-dimensional flat space, right, is given by this vector, what would be the speed?
Just root 13.
Yeah, it would just be the norm of that vector. So it would be 4 plus 9, it would be the square root of 13. So that's one real-life application of the norm idea, is that if you take the norm of a velocity vector, you get the speed. Okay, try this one. A rocket is something that moves through 3D space. So let's say we chose a 3-dimensional coordinate system and we've got some velocity. What is the speed of that rocket? Anybody have it yet?
Square root 34.
Yeah, square root of 34. Cool. Okay, next one. The velocity of an asteroid is given by the following vector. Its speed is 300. What are the possible values for z? All right, so let's talk about this. I've got to use my formula. And now I'm solving for z. Minus 50 squared minus 100 squared equals z squared. So z is going to be the square root of whatever this is, right? 90000 minus 2500 minus 10000. How many possible values do I have for z? 2. Yeah, because it could be plus or minus, right? And then when you square it, it still works in the end. So there's actually 2 different possible values for whatever z is. Did y'all already get that? Y'all were all working away at it. I couldn't tell if you were like done and working on another class or if y'all were still working on this problem. But that's the idea. Let's see. Okay, new definition. If you take the norm of a vector and the norm is 1, then that vector is a unit vector. If the norm of a vector is 1, you could also say the vector is normalized. Now, if I ask you, normalize this vector, that means I want you to find another vector that has exactly the same direction, but it's scaled up or scaled down so that the norm of the new vector is 1. And we use a little hat to tell you that it's a normalized vector. So there's the formula. That's how you normalize a vector right here. If I want to normalize this vector, I'm going to find another vector, u hat, and think about that for a minute. What are the entries of u hat? Mm-hmm. Yep. So u has a norm of 5 because you take the square root of 3 squared plus 4 squared. And then whenever I say that we are going to take my vector and divide it by its norm, you could also just think about multiplying by the reciprocal. And when we multiply a vector by a scalar, like we multiply the vector u by 1/5, we are going to multiply both of the entries by that scalar. So it's 3/5, 4/5. That's my normalized vector. And now if you go back and you take the norm of u hat, you should get 1. I'm just going to show you this and hopefully never have to use it again. But I know that this shows up in physics a lot. And so I want to actually say this out loud so that you see it in physics class and you know we're still talking about the same vectors. But since a vector is really at its heart just a list of numbers, some textbook publishers prefer to write vectors in rows where the entries are separated by commas. The reason they like to do this is because then your textbook doesn't take up as many pages and the textbook publisher saves money, and they, like they don't have to print as many pages. So it's like a revenue thing or a profit thing. They're greedy. They're greedy about their page space. I like to write vectors as columns, and so that's going to be my deal. I'm just going to use column vectors the whole semester. But in a similar vein, if you're in a physics class, I, J, and K are called standard unit vectors. And the vector I is the 1, 0, 0 vector. It's a unit vector in the x direction. The vector J is 0, 1, 0. It's a unit vector in the y direction. And the vector K is 0, 0, 1. So it's a unit vector in the z direction. And using this convention, a physicist can represent this nice, beautiful column vector as this gross, ugly, linear combination of standard unit vectors. I don't like that. I'm not going to do that, but I just want you to know that it's the same thing. And so, like, if you're in physics class, you might see something like 7i plus 8j plus 9k. And that's a physics thing. Find a 2D vector with magnitude 5 and angle 2 pi over 3 from the positive x-axis. So give that a try. This is two-dimensional, so see how much trigonometry you remember.
When you're doing these, does x always go above y when you're writing the vector?
Yeah, that's a good convention to keep. All right, so 2 pi over 3 is like in this direction, kind of. And I want the magnitude, or the length of the vector, to be 5. Now, that means this angle is pi over 3, or 60 degrees, right? And so if this is a 30, 60, 90 triangle, what is the shorter length here? Yeah. Yeah, if this were the unit circle, it would be 1/2. And since now it has a magnitude of 5, it would be 5/2. And then this would be perfect. 5√3/2. And then, like you said, for a two-dimensional vector, our convention is going to be to write the x-coordinate first. And this is going to be -5/2, +5√3/2. That's how we describe this vector in our 2D space. Stop me if you have any questions. By the way, on paper, are we supposed to have 50 minutes or an hour? 10:30? Okay.
They can go at 50.
It's too late. You should have lied to me to begin with. All right, suppose u, v, and w are three vectors that each represent a directed line segment, or an arrow. Together, these three directed line segments can be arranged tip to tail to form a triangle. What is u plus v plus w equal?
Down to 0.
Yeah. Yeah, Carter knows. You gotta think about my high-tech multimedia presentation. If I've got three vectors, u, v, and w, and if I line them up tip to tail like this, and they make a triangle, well then what would it mean to add these vectors together? You line them up tip to tail. And if it always makes a triangle, then you always end up where you started from. Conventionally, we always start from the origin, 0, 0, and the sum of these vectors would be 0, 0. So that's kind of a fun riddle, right? Everybody say yes, that was a fun riddle. Okay. Three forces with magnitudes of 400, 280, and 350 newtons act on an object at angles of negative 30 degrees, 45 degrees, and 135 degrees respectively. Find the direction and magnitude of the resultant force. So this is a problem from physics that we would normally solve by drawing a free body diagram. You say, this is my point mass, and I've got three forces. They've got some kind of magnitudes. I'm more interested in the angles. Let's say that my object is lying at the origin. Let me scoot it over. There's my object. Okay, so one of them is at negative 30 degrees. If it's acting on it at an angle of negative 30 degrees, I'm thinking about like right here. That looks like negative 30. And then 45 degrees is like right here. And then 135 degrees would be over here, right? And so let me list their newtons that you get. And there we go. So this problem is not a hard problem, but it is a long and annoying problem. I'm not a big fan. Here's how you do it. You first worry about the x component of the resultant force. And in the x component, we're going to have 400 times something of negative 30 degrees. The x direction is going to be the sine or cosine? Cosine of negative 30. Plus 280 times the cosine of 45 plus 350 times the cosine of 135. That's going to be my x component of the resulting force. And then you think about the y component. The y component is going to be 400 times what? Sine of negative 30 plus 280 times sine of 45 plus 350 times cosine of 135. Oh, sorry, sine. So cosine gives us the x component in the unit circle. Sine gives us the y component. You multiply by the magnitudes, of course. And now I've got the x component and the y component of my resulting force. That's not what the question is asking. The question is asking for the direction and magnitude. And so to find the direction, well, let's find the magnitude first, because the magnitude is easy. This is my force vector, the magnitude is going to be the square root of the x component squared plus the y component squared, right? It's the norm of the force. The direction, okay, the direction of the resulting force is going to be you all know this one? No? Okay. The direction is so weird. It's the arc tangent of y divided by x. And the reason for this is because you know the tangent of an angle is opposite over adjacent, right? And so if I've got some angle, theta, the opposite side is going to be the y component, and the adjacent side is going to be the x. And so I can write tangent of theta is y divided by x. And now if I want to get rid of the tangent, I have to use the inverse function. I have to compose both sides of this equation with the inverse function. Arctangent is the inverse of tangent. And so arctangent of tangent is just theta, and then arctangent of y over x becomes my right side. Unfortunately, this is not the end of the story. Does anybody know what the cruel trick is here? Do you remember this from geometry years and years ago? So, the cruel part of this story is if I have a positive x component and a positive y component, then my vector is in this first quadrant. It points in that direction, okay? What if I have a negative x component and a negative y component? Then it would point in the third quadrant in that direction, right? Okay. Now, if I have a positive y and a positive x, then y divided by x would be positive. We're good? What if I had a negative y and a negative x? Well, negative divided by negative would be positive. So whether I'm in the first quadrant or I'm in the third quadrant, I'm going to get the same theta. And that's kind of problematic because I won't be able to tell the difference between a vector in the first quadrant or the third quadrant. I'm going to get the same answer. In fact, this formula is always going to give me an answer in the first quadrant, even if your vector is really in the third quadrant. So anytime you are doing this problem and you see that your y component is negative and your x component is negative, know that arctangent is going to give you the wrong answer. Arctangent is going to give you something in the first quadrant. How do you solve this? What if y is negative and x is negative? What should you do to fix that problem?
Just like, could you add 180 degrees to your final answer?
You add 180 degrees to your final answer. Perfect. Or you add pi, right? A lot of times in calculus class, we like to work with pi. I guess in this problem, since we're giving you the angles and degrees, you could, just use degrees. So the asterisk here, the part that you have to remember is if x and y are negative, then add 180 degrees, or you add pi. And that will put you back in the third quadrant. It'll give you the same x component, but it'll make it negative, and it'll give you the same y component, but it'll make it negative. And that will give you the right direction for your resulting force. Okay, similar kind of idea. What if you have a positive x component, but a negative y component? That would put you, positive x, negative y, that would put you in this fourth quadrant. Okay, what if you've got a negative x component and a positive y component? That would put you in the second quadrant. Okay, but notice, whether this is negative and this is positive, or if this is positive and this is negative, regardless, you're going to get the same negative number that you plug into the arctangent function. And arctangent doesn't know which one was actually negative. It just knows that one of them was negative, and it's going to give you a value for theta in this fourth quadrant every time. So what do you do if you know that your vector really belongs in the second quadrant, but arctangent gives you an angle in the fourth quadrant? How do you fix that? You add 180. Okay, so if you know your vector should be in the second or third quadrant, be prepared, because this arctangent is only going to give you vectors in the first or fourth quadrant, but you can fix it by adding 180.
Why does adding 180 fix it?
Okay, so good question. It's a really good question. Let me find some space to draw. Okay, so let's say this is a 30-degree angle. And that means my x component is √3/2. My y component is half. If I now add 180 degrees, that's my new vector. This is a 30-degree angle. This x component is now negative √3/2, and the y component is now negative half. So you get the same value, the same absolute value of your components, but it makes them both negative. And the same thing, like I said, if you know your vector is actually in the second quadrant, arctangent's going to pretend it's in the fourth quadrant, but you can fix that by adding 180, because then it'll just point it in the opposite direction. Does that make sense? Okay. Cool. Yeah, in fact, I think it deserves a 3-minute aside to go on Desmos.com and discuss this a little bit more. This is the tangent function. And we say that this function has like multiple branches, if you want to call them branches. It's not a one-to-one function. When I say a one-to-one function, I mean like for every value of y, it can only be mapped to by one value of x. That would make a function one-to-one. One-to-one functions have inverse functions, and that's nice. But the problem here is that for a given value of y, like y equals 2, there's multiple different values of x that map to y equals 2. So this is not a one-to-one function. So whenever we say the arctangent is the inverse function for tangent, it's really only the inverse function of the principal branch of tangent from negative pi over 2 up to pi over 2. It's really only the inverse of that part in the middle. If you were trying to make an inverse function for the full tangent function, it might look like that, right? If you wanted to really reflect the whole thing over the y equals x line, it would look like that purple function. The only problem with the purple function is that it's not a function, right? The purple curve is not a function because if you give me a value of x, I can't tell you which value of y it should be. And so this is the problem. The arctangent function is just this middle curve. But what we really need, whenever I've got a negative value of x and a negative value of y, what I really need it to be is on one of these other branches and not the principal branch. Okay, I think that's all our time. Plot the following 2 points in 3D space. What is the distance between these points? And whenever I do this, I'm going to correct a mistake maybe I did last time because I don't remember. If we're going to plot something in 3D space, we need a 3-dimensional coordinate space, like these axes. We need 3 axes. And we're going to label them like this. I think this is the mistake that maybe I made last week. I sometimes forget that this is going to be x, this is going to be y, and this is going to be z. And so the mistake that I make occasionally is that I'll accidentally label the vertical one y, because in every other math class, up is always y. But the convention that everybody chooses to use is like this, where the xy plane becomes flat, like a tabletop, and then z gets to be the vertical direction whenever we talk about 3D space. This is sometimes called the right-hand rule. And so the right-hand rule means if you point with your index finger, that is the x direction. Then if you stick your middle finger out at a 90-degree angle, that would be the y direction, and then your thumb goes in the z direction. There's actually only 2 ways to label 3-dimensional space. There's the right-hand rule, and then alternatively there's the left-hand rule. This is sometimes called chirality, but the chirality that we choose in the conventional sense, like all the textbooks are written with this chirality, is with the x, y, and z. So let me look and see what I did last time, because I don't even remember. Did I do this? Did I not do this? It's an xy plane, but I think there was a point where I actually tried to draw me some space. Yeah, oof, terrible. Okay, so what's the problem with this? If I point in the x direction with my index finger, and then I point in the y direction with my middle finger, then my thumb doesn't point in the z direction. My thumb is pointing in the negative z direction, right? And so that's the left-hand rule. That's where if I point with my left hand in the x direction, and my middle finger goes in the y direction, and then my thumb would go in the z direction. So this is left-handed chirality, but that's not how we normally want to do it. Normally we want to do it with right-handed chirality, so it should have been more like this. Okay. Now, once I've got my axes, if I want to plot the point 1, 2, 3 in space, you just do your best. I know it's not going to look good, but that's fine. This is not art class. So I'm making a little dot that's 1 in the x direction, 2 in the y direction. And I'm imagining that that dot is in the flat xy plane. And then now I need to go up 3 units in the z direction. And then this is the hard part. What would it look like for this thing to be up 3 units in the z direction? Maybe right here? I don't know. But that's my best attempt at placing that. And then for the other one, looks like we need to move 3 in the x direction, negative 3 in the y direction. So we get a point like right here on the xy plane. But then now we need to go negative 2 in the z direction. And that lands us like right here. But like I said last time, you really need to have a good imagination, because whenever I look at this, it doesn't really look to me like this is at 3, negative 3, 2. It looks like it's sitting on the y-axis, you know. But you have to look beyond my drawing
into what I'm trying to say. What is it? Do what I say, not what I do. It's like, imagine what I want you to imagine, not what I draw. Okay. What is the distance between these points? Okay, so we talked about the norm of a vector last time. And now, if I want to figure out the distance between 2 points, let's say this is point A and this is point B, I'm going to come up with a difference vector that I get from subtracting these two coordinate triplets. And so if I do A minus B, that's 1 minus 3, which was negative 2. Two minus negative 3 is 5, and then 3 minus negative 2 is 5. So this is my difference vector. This is my list of numbers that tells me the differences between their coordinates of point A and B. And then if I want the distance between those 2 points, I just need to find the norm of this vector. And of course, the norm is going to be negative 2 squared plus 5 squared plus 5 squared. And then you take the square root. If you tell me your answer is square root of 54, that's fine. I will still give you full credit for the square root of 54. If you want to be really fancy, this would be 3 times square root of 6. But you don't have to do that. You will still get full credit on an open-ended question if you write square root of 54. But if it's a multiple choice question, I might be especially cruel and list your multiple choice correct answer choice as being 3 times square root of 6. Just for fun. Yeah. Okay. Suppose the 3 points below are the vertices of a triangle. Determine whether the triangle is a right triangle, an isosceles triangle, both, or neither. Ben, how would you solve this question? How do you answer this question?
Find the side lengths first,
Mm-hmm.
doing the difference vectors for all of them, and then figuring out if they were sides of equal length or not to get the isosceles part.
Mm-hmm. How would I figure out whether it's a right triangle?
Could you do some with projections onto the x-y?
You're making it way too hard.
Yeah, I know I am. I don't know how to do it.
You just check Pythagorean theorem.
There you go. Yeah. Yeah, so Ben had to start off in the right direction, especially for finding out whether this is isosceles. Ben says, call this point A, B, and C, and then let's calculate some difference vectors. And now, whatever our triangle looks like, I don't know, just pretend this is our triangle. Between point A, B, and C. The norm of U is going to be that side length. The norm of V is going to be that side length. And the norm of W will be that side length. And now if I know the side lengths of a triangle, what does isosceles mean, Daisy? What is an isosceles triangle? What's special about that?
That is not a right triangle.
No, okay, so Aaron, what is an isosceles triangle?
When two of the sides are equal.
Yes, when 2 of the sides are equal length, that makes it isosceles. And so yeah, that's what you'd need to do. You just need to take the norms of these difference vectors and then say, are 2 of the norms exactly equal to each other? And then Carter told us how to answer the last part of this, which is it a right triangle? Well, you would have to take the two smaller norms, square them, add them together, take the square root, and ask, is that equal to the larger norm? To figure out if it satisfies Pythagorean theorem. Because obviously, if those norms satisfy Pythagorean theorem, then it's a right triangle. And if not, then no. Questions about how to do that? Does that make sense? Okay, there's a few of those on your homework if you want to practice that. The parametric equation for a line looks like one of these things. So there's two equal signs, but there's three different equations for a line. I want you to just accept that these are exactly the same. Whether or not I have a vector of constants plus a parameter, this variable t is called a parameter, times another vector with constants. Or if I have one vector where each of the entries looks like a constant plus a constant times the parameter t. Or if I choose to write the same vector but I write it out horizontally, keep in mind that those are really the same thing. And that's what we call a parametric equation for a line. Let me show you an example. Let's actually work exercise 10 and then I'll show you an example. 10 says, find the parametric equation of the line that passes through the point 0, -2, 3, and is parallel to v. So in this equation, the x0 with the little subscript is going to be any point along the line, the x coordinate of that point. And then the y0 is going to be the y coordinate of the same point. And then the z0 is going to be the z coordinate of the same point. And then the other thing exercise 10 tells me is that I want my line to be parallel to this vector v. And if I want it parallel to the vector 1, 3, 5, that means A is 1, B is 3, C is 5 in the parametric equation from that line. So let me go ahead and write the answer now. Zero plus 1t, and then -2 plus 3t, and then 3 plus 5t. Okay. So the reason this works is because if I choose t equals 0, then I can guarantee that point belongs to my line. And then it's parallel to v. My line is going to end up parallel in space to this vector v, because as I choose different values of t, it's going to add different multiples of that vector to the original point I'm starting from. Let's plot this. Now, my favorite website of all time, Desmos.com, only graphs things in 2 dimensions. My least favorite website of all time, what is it called? I can't remember. GeoGebra. Hate GeoGebra. Have you guys ever used this before? It's horrible, right? Like, I don't know if this happens to you, but every single time I'm trying to type in a really long, really complicated equation, it just deletes it, like just randomly, just poof. So, not a fan. But this is, I think, what the equation was. I can double check my numbers. -2 plus 3t, 3 plus 5t. Okay, cool. So yeah, you can just type it in exactly as a parametric equation for a line, and GeoGebra should be able to graph it for you. You'll notice that GeoGebra is using that right-hand rule, right? X is in that direction, Y is in that direction, Z is in that direction. So I'll try to stick to using that. Okay. What a beautiful line. Okay, write the parametric equation for a line passing through these 2 points in 3D space. How should I do this, Mikey?
Start by making a point A, point B.
Okay, yeah, let's label them. What should I do next? Okay.
Find the vector for the distance between the two.
Yeah, or we could calculate the difference vector, right? There's going to be some vector where I take a minus b and get a difference vector. Call it just lowercase v if I want to. Connor, what do I do next?
You write 3 minus 0, 4 minus 6, and 0 minus 1.
Okay, so all right, so I can actually calculate this difference vector. 3 minus 0, 4 minus 6, 0 minus 1. Okay, and then what do I do, Connor?
Then you
So just to remind you, my answer should look like this. Like my final answer should be a parametric equation for a line. And that means it's going to look something like this. The question that's being asked when you see this type of question is basically the question of what is x0, y0, z0, and what is a, b, and c? Lexi, what is A?
Like labeled up there?
Not capital A. What is lowercase a? What number should that be? Okay, that's fine. I'll tell you. So here's one way I could solve this problem. Oops. So I borrowed the a, b, and c constants from the difference vector, and I borrowed the x, y, z with subscript zeros from my capital B point. Now, if I set my parameter t equal to 0, say t equals 0, then I get the vector 0, 6, 1, which puts me right here. What value would I choose for lowercase t if I want to get back this vector? 1. And so I can go between this point and this point by allowing t to go between 0 and 1, right?
Because your ABC is like your slope, right?
Yeah. Now, what's another way I could have solved this? There's another solution here. At least one other solution.
Can you do 3, 4, 0, 6, 0, 6, 1?
Perfect. Yes. Alex is right. I chose the coordinates from the second point, but there was no reason not to just choose the coordinates of the first point. Because, I mean, calling them the first point and the second point was an arbitrary choice to begin with. I could have just called it like this. And now if I set t is equal to 0, I get this point back exactly. What do I set t, my parameter, equal to if I want to get this point on my line? -1. Yeah. Cool. Yeah, so for this type of question, you got 2 points, you want to draw a line through them. You find the difference between the points. That's the coefficients that you're multiplying times t. And then you find either point to use the coordinates for to base your line off of. And that will work. Determine whether the following 3 points are collinear. Collinear means they all lay on the same line in 3D space. And that doesn't have to be true. You could have, any 2 points fully and uniquely defines a line. There's only one straight line that goes between any 2 arbitrarily chosen points in space. But if I have 3 points, then it's almost definitely guaranteed that the third point, if randomly chosen, is not going to be on the line. But I didn't choose these points randomly, so we'll see. Use the first 2 points to formulate a line as a parametric curve, or the parametric formula for a line, with parameter t. Then see if the third point is given by any specific value of t. So that's what we'll do. Just following instructions right now. These 2 points, we're going to call them A, B, and we'll call this one C. But I first need to find a difference vector, right? A minus B, like this. And then I can write my line, the line that goes through these 2 points, as, I don't know, let's say 0 minus t, negative 2 minus 3t, and 3 plus 3t. And the question is there any choice of t that makes this line equal to this point? Because if that point C lies on that line, then you should be able to choose a value of the parameter that gets you there. Okay, so let's think about it. If 0 minus t is equal to 3, then t is negative 3. Okay, so now let's assume t is negative 3. Negative 2 minus 3 times negative 3 is negative 2 minus negative 9. That's negative 2 plus 9. Is that 7? Cool. So it works out so far. We also have one more we have to check. 3 plus 3 times negative 3. 3 plus negative 9? Is that negative 6? Yes. Okay, cool. So if I choose t equals negative 3, then that gives me a point on my line that corresponds with the third point, which means those 3 points are collinear. They belong to the same line. Does that make sense, how we did that? Why we did that? Okay. All right. New vocabulary word for you guys. 2 vectors are parallel if one of the vectors is equal to the other vector times a scalar constant. So k is a scalar. K is just a number. U and v are vectors. So exercise 13 says, determine whether the following 2 vectors, I'm going to name them u and v, determine whether or not these are parallel. Well, if they are parallel, I should be able to write u equals k times v. If they are parallel, then that should make sense. Are these parallel vectors? Yes? What value of k solves that equation then? negative 1/2. No, sorry, negative 2. Connor said that so confidently. It threw me off. Just kidding. If k is negative 2, then it's perfect, right? There's not always a value for k. Most of the time, there's not a value of k that makes that work, because most of the time vectors aren't parallel. But in the case where vectors are parallel, you should be able to find a value of k that makes it work. And if you do find a value of k, then that means the vectors are parallel. All right, this time, look at those. Is there any way these are parallel vectors? Are these parallel vectors? Why not, Matt?
So for the first two, you can multiply, like if k is set to equal, I think, 4/3, then that works for the top two, but for the bottom one, 4 times 4/3 doesn't equal 7.
Perfect. Yep. If I look at the top entries, k has to be 4/3. But if I look at the bottom entries, 7 is not equal to 4/3 times 4. So there's no value of k that makes it work. So here's another question that might seem a little bit familiar to you, a little bit of deja vu. Determine whether or not these 3 points are collinear, whether they lie on the same line or not. But this time, my instructions say, first, I'm going to define a vector u using the first 2 points and another vector v using the last 2 points. And then another way I can check to see if points are collinear is I can see if those 2 vectors are parallel. Because if they are parallel, then this means they're collinear. But if you get 2 vectors that aren't parallel, then that means, of course, they're not collinear. So I'm going to label my points. So my vector u is going to be a minus b. V is going to be b minus c. So this is going to be 0 minus 1, negative 2 minus 1, 3 minus 0. Negative 2, negative 6, and 6. Okay. Now, you got to remember this equation. If u and v are parallel, then u equals kv. Are u and v parallel? Yes? What is k? 1/2. So yes, these are parallel vectors, and since those difference vectors are parallel, the points are collinear. Any questions at all so far? All right. So this is just more of the same. There were 2 different methods we could use to figure out if 3 points are collinear. The first one we tried was making a parametric formula for a line, and then choosing a value of the parameter that would give us the 3rd point. The second method we used was finding the difference vectors and testing to see whether they're parallel. With this exercise 15, you can do either one. It's up to you. Pick one method that you like the best, and then just go with it. Let's use the parallel method for this one, but you can, like I just said, you can do whatever you want. So the vector a minus b is going to be this. The vector b minus c is going to be this difference vector. Okay. And then what we're saying is I want these 3 points to be collinear. And that means for these different vectors, I really want them to be parallel. Let's talk about what needs to happen in order to make these two vectors parallel. First, k has to be equal to what? 1/2. And if k is equal to 1/2, that means -3 is equal to 1/2 times 1 minus y, right? That means y has to be equal to what? Yeah, Connor should have phoned a friend. Sorry, this is a cutthroat class here. You just reminded me of the whole Who Wants to Be a Millionaire thing. Do they still air that? Is that still TV now? Who Wants to Be a Millionaire? No. That was on the TV back in the day. Back in like 1999. The last thing we need is z. We can figure out z by saying 3 is equal to k times -z. So that means z is equal to what? -6. Okay, so then we answered our question. If we really want those 3 points to be collinear, then we know what values of y and z we've got to plug in. And again, there was another way to do this that I haven't shown you, which is you can do the parametric formula for a line. You can construct that using the first 2 points, and then you can choose a parameter that would get the x coordinate to the number 3, and then you get the y and z coordinates by using the same parameter. Exercise 16, find the midpoint between these 2 points. How do I find the midpoint?
Divided by 2. Or find the length of the line divided by 2.
Do I need to find the length of it?
The distance between the 2 points divided by 2.
I don't even need to find the distance, though. I'm not going to do any work if I don't have to.
The difference between each like individual coordinate divided by 2.
Yeah. Although, no, you're wrong. It's not the difference between the coordinates. Sorry, I'm way too quick to agree with you guys. We are not finding the distance between the points, and we're not finding the differences between the coordinates. Blake.
Can you use the midpoint formula of each point?
Yeah. What's the midpoint formula?
Try to remember that. Is it x squared plus or x2 plus x1 with the square root over everything?
Oh, no.
No, not that word.
It's just like x1 plus x2 over 2.
There we go.
And then y1 plus y2 over 2.
Matt's got it.
Just add
I just got to average them. Yeah. I got to add the 2 x coordinates together, divide by 2. Add the 2 y coordinates together, divide by 2. Add the 2 z coordinates together, divide by 2. So my midpoint is going to be, what's my x coordinate? 2. And then my y coordinate? 1. And my z coordinate? 1. Very good, yeah. So what was going on here is I was taking the first x coordinate plus the second x coordinate, divide by 2, and this gets me the midpoint x coordinate. Same thing for y and same thing for z. Now, the rest of the question says, after we do that, Find the point that has traveled 90% of the distance from point A to point B. How do I do that?
Do x1 plus x2 like times point nine.
No.
Would you divide it by a different number that I want to know at this very moment?
I'll just tell y'all, you're all are on the right track. But you know, this midpoint formula that we're looking at, another way I could have written it is maybe something like this. 0.5 or heck, I could call it 50% times x1 plus 50% times x2. That would give me the midpoint. So what I'm going to do now for the 90% point is, instead of giving it 50% of x1 plus 50% of x2, how much x2 should I give it?
10. 0.
What's
-10.
90. Yeah, we're 90% of the way to x2. And so that means we're still holding on to 10% of x1. And you guys know how percents work. I could type in 0.1 times 0 plus 0.9 times 4 to get my x coordinate for this 90% point. And so my coordinates here are going to start off as 3.6. And then I would need 0.1 times -2, which is like negative 0.2. And plus 0.9 times 4, which is 3.6. So altogether 3.4, I think. And then the last one is like negative 0.6. Okay. But that's how you do it. If I said I only want it to have traveled 20% of the distance from point A to point B, then I would multiply point A coordinates by what? 80%. Because I've only traveled 20% of the distance. I'm closer to point A, so it gets more of a weight in my weighted average. If I'm closer to point A gets a larger weight in the weighted average. If I'm closer to point B, then point B gets a larger weight in the weighted average. Okay. So in case you didn't know what a sphere is the set of all points in 3D space that are equidistant from a center point. So that means, choose a point out here in space, and all of the points together that are the same distance away, you get to choose what that distance is. Let's say that distance is 5. So all the points in space that are 5 away from the center, they form a spherical shell. I should just call it. They form a sphere. And so the question is, which equation would describe a sphere with a particular center and radius? I'm going to call the coordinates of the center point A, B, and C, I'm going to call the radius R. Now, equidistant. We know the distance formula, right? The distance formula says, if I want the distance from a point XYZ to a point ABC, I'm going to do the square root of x minus a squared plus y minus b squared plus z minus c squared. That's the distance, right? And this distance should be equal to my radius. Normally, when you see this, we will square both sides and scoot that over there. So normally this is what it looks like. But this equation is going to be the equation that describes a sphere in space. Okay, write the equation describing the sphere with the following 2 points as endpoints of a diameter. A diameter is a line segment that goes from one point on the sphere to another point on the sphere. It's a straight line segment and it passes through the center of the sphere. That makes it a diameter. So if those are endpoints of a diameter, how would I find the center of the sphere? Alex said it's the midpoint, yeah. So the center of the sphere is going to be the midpoint halfway between these 2 points. Yeah. How would I find what the radius is? For my sphere.
Use one of the points as your x, y, and z, and then the center is a, b, c, and then vice versa. And then put it to the equation itself.
Could you just find the distance from one of the points to the center of the
Mm-hmm. The radius is the distance from any point on the sphere to the center. We've got 2 points on the sphere that we can use. And so we just have to find the distance from one of those points to the center. Another option is you could find the distance between those 2 points and then divide it by 2, because the diameter is twice the radius. So I like dealing with whole numbers. I don't like fractions. And so I'm going to avoid using fractions until the very end, I hope, by just finding the distance between these 2 points, finding the length of the diameter. And so that is going to be the square root of 1 minus 0 squared plus negative 2 minus 1 squared plus 3 minus negative 7 squared. So that's the square root of 1 plus 9 plus 100. Square root of 110. That is only the diameter, though. So the radius is half that. The radius is half the diameter. Okay, so now I'm ready to write my equation. Because I have the center of the sphere, and I've got the radius of the sphere. Oops, sorry, that should be a y. And then on the right side of my equation goes the radius squared. So that would be 1/4 of 110, or I could call it 1/2 of 55. 55 halves. bad circle. All right, so that takes you through just about every little geometry problem we have on the homework. We haven't started doing any calculus yet. I realize that. We will eventually do calculus in this class. But I think the purpose of like this first section that's normally taught as part of Calculus 3 is to try to make you familiar with these ideas of like points in space and calculating the differences between points as vectors that have, you know, length and a direction, and I mean, I guess that's the main ideas. Because eventually we will do calculus in 3D space. And that will be slightly more exciting. Let me go ahead and plot this sphere on GeoGebra, because, you know, sometimes that's fun. I can type in x minus 1/2 plus y plus 1/2 squared plus z plus 2 squared is equal to 55 halves. Okay. Wow. And we can even see too, if I put the point 1, -2, 3, and also 0, 1, -7. We can just verify that these were supposed to be endpoints of a diameter, and that might be a little bit hard to tell, but at least they look like they're on opposite sides of the sphere. And they're at least on the surface of the sphere, which is good. You know, this is a good way to check your answers, right? Like if you're working through problems, check your answers in GeoGebra. You can plug in equations for lines, and you can plug in the points and make sure all the points are on the line or not or whatever. And one way I would know if I made a mistake during all of that arithmetic, I could tell I made a mistake if the sphere didn't actually include those 2 points. But it looks like everything's all right here. So, questions, thoughts?
I have a question from a previous problem from Friday.
Mm-hmm.
So the ones where we talk about with the 3 forces of magnitude acting on the object,
Yeah.
does the degree indicate which direction the object is going or which way the force is being applied? So if it says like 300 newtons at 30 degrees, does that mean it's going into quadrant 3 or into quadrant 4?
That's a great question. I know what you're asking, and it is a really good question. Because I probably drew it a particular way. Because I know I said like in green it was acting on the object at an angle of 45 degrees, and the way I drew this arrow shows the force like acting on it like this. I don't know what the right answer is because I'm not like a physics teacher, so I don't really deal with this very much, right? This is the one like physics related question I do all year. And so I don't know, if I say it acts on an object at an angle of blank, I don't know if the physics convention is having it arrive at that angle or if it's supposed to be like, I don't know. That's a great question. The longer answer to this is, I used to be an engineer with a very mild grasp of how mathematics worked. Okay, like I wasn't always a math person. But working as an engineer, I would have like a pretty good idea of what I should be doing with the math every single time I got an answer, right? Like I work at my desk for an hour and I got an answer to my question. I would always think, does this make sense? Okay? So if I'm expecting forces to act on my object in this kind of manner, then whatever answer I get for the resulting force, like the direction and magnitude, I expect it to be moving that way. And if I got an answer that was moving in the opposite direction, that would probably be an indication that I drew my arrows going the wrong way. You know what I mean? So that's what I would say is like the lesson for real life practice is always like use your gut, your intuition to check the answers that you get and see does that even make sense or not. Especially if you're using AI to do your work, right? Like you're a real life engineer, you have AI answer a quick question for you. AI gets things wrong probably like 10% of the time, right? So you get lulled into the sense that AI is doing everything correctly and then you trust it too much and then it'll bite you. But always use your own critical thinking skills. Use your sense of intuition to say, is AI giving me the right answer or is it giving me a completely wrong, crappy answer, you know? So I hope that answers your question. If I give you this on a test, like I could give you any of the practice problems on your next test, I will draw a picture for you. Okay? I'll draw a picture like this on your test. And so you won't have to wonder about which way to draw the arrows. On your homework, choose a convention that works for you and then make sure that your answer makes sense given your own convention. Whatever makes sense to you. Good question. Y'all are real quiet today. This may just be super easy though, because y'all are used to hard math classes and this is probably the easiest thing you've ever done, right? No? I can't tell you guys. This is my first year. If you don't tell me, I'm just going to make an assumption. Seriously, was there anything that was hard? Do you want me to work another example? Do you want me to work something from the homework?
That was hard.
This was hard?
I think that was the hardest problem.
Yeah, I don't think
Okay.
I don't know about everybody, but I know a lot of us haven't been through like a true class, and so like we're trying to learn everything.
Okay. Yeah, so let's talk about this a little bit more then. So what was the first thing we did? We tried to draw the picture, and this is the best picture I have for you. You can always ask Craig if you want a better free body diagram. So we've got three forces. We drew the three forces. Again, I'm not 100% sure if this green arrow was supposed to be 45 degrees, and so I draw it at the 45 degrees, and then it's acting on the object, so I put the arrow towards the object. Or maybe the force was supposed to be moving in that direction, like Carter was suggesting. Maybe I should have drawn the arrow over here, so that I was pushing on the ball at a 45 degree angle. I don't know. Maybe a better way to do it is this. Maybe the best way to do it would be to like draw the force kind of originating from the ball. You know what? We don't even have to wonder. Let's ask. Free body diagram. Let's see how other people do it. Okay. This is the convention we're going to adopt. Sorry for the confusion. Sorry I messed it up last week. We're going to draw the forces emanating away from the object. That's probably the right way to go. I was imagining in my head like something like pushing on it. And so that's why I drew the arrows the way that I did. But
Pushing though, wouldn't you have to like add 180 to each of your degree measures to get the right answer? Like you just have to you just adjust your answer based off like what makes sense on the diagram you make.
yeah, yes. Your answer always has to make sense. Okay, so that's better. And now let's talk about what do I need to fix in order to make this work right. So I've got 280 acting at 45 degrees. I've got 400 acting at negative 30. And I've got, okay, so the diagram is correct. When we talk about the x component, we always use cosine of the angle when I multiply the magnitude of the force, because on the unit circle, right, we always use cosine for our x-coordinate. Do you remember the unit circle? This was what Blake was asking about, maybe because you were referencing like trig class. Like, what do we learn in trig class?
That's very true.
Did you not take trig?
I did, and I don't remember the
In trig class, we say this is called the unit circle because this is where x is equal to 1, this is where y is equal to 1, this is where x is negative 1, and that's where y is negative 1. And if I want to know for some angle what this distance is, this distance would be cosine of theta, and this vertical distance in the y direction would be sine of theta. So I can break down my vector into an x component, which is always multiplied by cosine, and a y component that's always multiplied by sine. Because x and y are directions that are perpendicular to each other, so I can draw a little 90-degree angle, and then I've got my right triangle. And so that's why here I've done the magnitudes times the cosines of the angles to get the x component. And then the same thing, I did the magnitudes times sine to get the y component of each of the force vectors. And I add them up. Forces just add together. And it's okay if I break them into components and then add them together. That is still perfectly all right with Isaac Newton. And once I have the sums of those components, I've got the resulting force. And the only problem here, the only last thing we have to do is we actually want to find the direction and magnitude of the resulting force, not the x and the y components of the resulting force. That's actually pretty easy to find the x and y components of the resulting force. Our next discussion that we had last week was about how to find the magnitude and direction. The magnitude is not so bad. The magnitude of the resulting force is the square root of the x component, which is all of this stuff added together, squared, plus the y component, which is all of this stuff added together, squared. That gives you the magnitude. The direction is the last tricky part, because the direction is going to be given by the arc tangent of y divided by x. And again, the reason for that is because tangent is opposite over adjacent. And I'm so sorry if I'm like, I don't know, making this way longer than I need to as a lesson, because again, this is my first year. I don't know if you guys are like geniuses and y'all are like bored in class, or if y'all are, you know, dum-dums and y'all are just lost in class, or if y'all are somewhere between, because I stare out and just sometimes just blank stares look back at me and I can't really tell what I'm doing. But sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. That's the definition of what those trig functions mean. So if I want to know about the direction of a particular force, I would need to say, well, the tangent of that direction has to be equal to the y component, because that would be on the opposite side of the triangle, divided by the x component, because that would be on the adjacent side of the triangle. So tangent of theta is equal to y over x. The arctangent function is defined as the inverse function to the tangent function. And so if I take this equation and I take the arctangent of both sides, the arctangent cancels out the tangent, and I just get theta, and then I have arctangent of y over x. Now, this is a great formula, But arctangent only has a range that goes from negative pi over 2 to positive pi over 2. Or in other words, negative 90 degrees to positive 90 degrees. That's the range of arctangent. So that means this formula is only going to ever give me an angle that's between the negative y-axis and the positive y-axis. It's never ever going to give me an answer in quadrants 2 or 3. It's only ever going to give me an answer in quadrants 1 or 4. The reason for that is because if I ended up somehow in quadrant 2, I would then have a negative x value and a positive y value. And if this is positive divided by negative, it's going to be a negative number that I plug into arctangent. And arctangent can't tell if this negative number is from a negative x value, or maybe it was from a negative y value and a positive x value. So in other words, your arctangent function can't tell the difference between quadrant 2 and quadrant 4. It thinks these are the same. And to handle that, it just only gives you outputs that appear in quadrant 4. Same thing goes over here. If I have a positive x and positive y, I'm in quadrant 1. If I've got a negative x and negative y, I'm in quadrant 3. But even over here, if I have a negative number divided by a negative number, that becomes a positive number. So the input to the arctangent function is a positive number, and it can't tell the difference. It doesn't know whether it's in quadrant 1 or 3, so it just tells you you're in quadrant 1. The way you fix this is you add 180 degrees, or you add pi, right? I should say, if you should be in quadrant 2 or quadrant 3, then add 180 degrees. Because if you should be in quadrant 2, this formula will put you in quadrant 4. You add 180 degrees, you're back in quadrant 2. If you should be in quadrant 3, that formula will put you in quadrant 1, but if you add 180 degrees, then you end up back in quadrant 3. And 180 degrees is equal to pi. Questions? No? Okay. If you are using software, let me show you how this looks in Excel. If I say it's not arctangent in Excel, it's atan. And then let's choose some y coordinate divided by x coordinate. So this is going to be my y coordinate and my x coordinate. Let's say that I'm in quadrant 1, so I need 2 positive numbers. Here is an angle in radians in quadrant 1. What if I'm in quadrant 3? So I've got a negative number and a negative number. I still end up with an angle that's in quadrant 1, okay? What you can do to fix this in most programs, like Excel for example, is instead of using arctangent, I'm going to use a function called arctangent2. And the great thing about arctangent2 is that arctangent2 gives you a place to enter your x coordinate, comma, enter your y coordinate. And now it's going to give me the correct angle, even if it happens to be in quadrants 2 and 3. So Excel has thought about this, and they fixed the problem by creating a new function called atan2.